Okay. Right, so we are looking through these questions on the fundamentals of reactions. And I must say, a lot of this should occur to you as things you already know from chemistry, right? In your courses in chemistry, you've talked a lot about how the different types of atomic structures influence the reaction rate. You've talked about the concepts of conversion, and you've looked at the extent of the reaction. You've talked about reaction equilibrium and so on. In this course in particular, we are interested in the reaction rate, right? It is critical to us as chemical engineers to be able to determine the rate of the reaction accurately. And in fact, you'll find that the rate of the reaction is not any one thing. So if you look at a reactor, you've got multiple zones in that reactor, and you've got regions where the rate is much different to other regions in that reactor. In fact, let's have a look at some of the material. Right, so that's the scale we are talking about, right? So there isn't a little man here that helps you get the scale, but you can see from the stairs here the approximate size of this. And in fact, this is a fairly small reactor, and typical volumes range in the 40 cubic meter to 100 cubic meter, even 200 cubic meter range. So that's the size of reactor we are talking about. And you can imagine in such a relatively large space, you will have significant variations in, for example, the temperature across this unit. So you'll have different temperatures. So it might be that there's a feed point here and you've got a cold stream coming in. And due to the reaction, the reactor itself is at a higher temperature. So you can imagine easily a temperature difference across the reactor. Then, of course, as things are flowing through, there are pressure variations across the reactor and so on. So there's a lot of difference across this reactor in terms of the temperature and pressure, and hence the concentration. The reaction itself is going to change the concentration. So if everything is entering at this point and then it's flowing down the reactor and then exiting out here, you can easily imagine the concentration of reactant is high here and it goes down and it gets to lower values down here. So everything is changing across the space. And that complicates our attempt to estimate the reaction rate, right? We would like a really nice, easy reaction rate. We want to look at the reactor and say, okay, the reaction rate is 1,000, whatever that means, right? But it's not ever going to be 1,000 everywhere. And a lot of what we'll be doing in this course is just coping with the fact that the rate is differing across the reaction volume. And we have to unpack all the reasons for that rate differing across the space. It basically all comes down to estimating the reaction rate also. Anyway, this is showing on the upper deck that you might be doing some operation there on the top of the reactor. This is showing some of the ports that you might be using for that reactor. You'll have different entry points for the different types of species. You might have special ports where you are, for example, metering catalyst into the reactor and so on. And then in terms of a simpler picture, you can see some of the controls here. So you can see, for example, if you have a liquid phase reaction, you may have something that's trying to control the level in the reactor. So you can see level control here. You might have temperature control. So you can see a cooling jacket here. And you've got stirring and so on. So those are just some examples of things that go on in the reactor. And we'll be looking at many different types of reactor as we go. You will notice some general characteristics. So in fact, the temperature is such a critical variable in reaction engineering that most reactors even look like heat exchangers. And you can see here, this basically looks like a shell and tube heat exchanger. And in fact, the only difference here is that if you zoom in on the tubes, you can actually see little particles here. And that's because we've got catalyst loaded on the tube side of this reactor. So it's basically a heat exchanger packed with the catalyst. And so the reaction is happening in the tubes. And on the shell side, you've got some heating or cooling medium. So that's basically what we are trying to design. We are trying to figure out how big must we make this reactor? How long do we want the components to stay in that reactor? What kind of mixing is going to go on there? Because obviously the mixing is quite important. And that is a bit different to what we talk about when we think about contacting the different reacting species and so on. So we'll be unpacking each of those things as we go. And so we're starting, of course, with the reactor reaction rate. Okay, so before we jump in there, any questions or comments so far? Okay, so we want to now understand the reaction rate, and I'm going to have a couple of quick sketches in here. So, and I'm just drawing with the mouse, so excuse the drawing here. So let's say we've got, well, let's stick with the tutorial question. So we've got 2 of A reacting with 1 of B. So let's say that's A, and then that reacts with B. And so these 2 combine in some way, and they give us 2 of C. Right, so this, of course, I'm intending to kind of hint at molecules here. So 2 molecules of A reacting with one molecule of B, giving us 2 of C. And in terms of our engineering questions, we want to know what's the rate of that reaction. And when we talk about the rate, there are, in fact, a number of concepts that are compressed into that word rate, right? That word rate is quite an interesting one, because there are several parts to estimating a rate here. Number one, if I ask you, what's the speed of this reaction, right? And if you look at the question, it gives us the reaction equation, and it gives us this kinetic rate constant. And so we can think, well, it looks like there is some time influence here, but how is this a speed, right? And so we can think about, what do we mean by the speed of this reaction? Number one, is it the amount of time it takes for this to complete? So you could think about, you've got 3 molecules that need to combine here and give us some product there. And then you've also got a sequence of steps that will influence that. So as part of the reaction, what may happen is that some bonds will break or some bonds will form. So it might well be the case that a bond has to form between the 2 A molecules, and then some bond has to break in the B molecule. So a bond has to break there. And then there might be some combining of these bonds with this new complex. And then the whole thing reforms and breaks apart into the 2 Cs. So what I'm trying to say here is that there might be a sequence of steps that have to happen before this reaction happens. So a number of internal bonds, right? Think of this, maybe these are benzene rings. So if A is a benzene ring, we can easily imagine there might be a double bond that has to break in each of these before they can combine, and so on. So there may be a sequence of steps involved there. And so each step may take its time. And obviously those are on very small time scales. Those are not even microseconds. Those are probably on the order of 10 to the minus 14 in that time range. So you've got some sequence of steps that may take a specific amount of time to complete. And so coming back to the question, what's the speed of the reaction? So you could say, well, if this is taking maybe 7 times 10 to the minus 14 seconds for one such cycle to complete, right? Just as an example. So if it takes that amount of time to complete, what's the speed then? Is it 3 molecules per 7 times 10 to the minus 14? Sorry, there's some construction going on next door. 1 second. So is it the speed at which molecules are converted? Now, that may be the time it takes for this particular combination to happen. But how often does this happen? That's a different question. So for that, you have to think about the space in which all this is happening. So you've got a collection of A molecules, right? It's not the case that we are able to put 2 little A molecules in our reactor and sit there and wait for them to react, right? What actually happens is that we have a whole sea of A molecules and a whole sea of B molecules that we feed into the reactor. And then we have to wait for 2 of those to combine and react with the B and give us the C. And then what will start happening over time is that C will start to accumulate in there. Right, so this is actually what's happening. And so you can see from this picture then that the probability that this event is going to happen is dependent on the rate at which these molecules are banging into each other, right? It might be that if the mechanism tells us that the 2 A molecules have to combine first, then we first need A and A to knock into each other. And then we'll need a B to come along and knock into that complex. So you can see there's a certain probability that A molecules will collide, and then there's another probability that B will collide with that. And then there's also a question, is there enough energy in the system to then convert that into component C? And so you can see there are a number of things that go into determining how fast this is all going to happen. And of course, the collision rate is again affected by the temperature. So if the temperature is higher, everything is banging around very quickly. If the temperature is lower, then compared with that, the molecules are not moving around as quickly, and so the rate will drop. So you see, there's this influence of probability also. What's the probability that this particular cycle is going to happen? So the speed of the event itself, right, the fact that the reaction is happening, that is tempered by the probability that there will even be this combination in the first place, right? And so there's the influence of probability, then there's the speed of the event itself, and then there's the fact that all these molecules are bouncing around in the same space. So all of this thinking is summarized in this reaction rate, right? So, and in fact, okay, here. So we define RA, or in fact, we define RI. So for any component, we define R to be the rate of formation of that component, right? So we simply say it is the rate at which a component is being formed. And the way we write that, maybe the units give us something of a clue here. Right, I see there's a message in the chat, which I'll get to just now. So our rate of formation of component A has the units of moles per second. Moles per second. And it's also per cubic meter here. So we'll come to the per cubic meter just now, but it's moles per second because this is now not trying to figure out what is the probability, what is the speed of the, how long does it take for these bonds to break and reform. It's not trying to work out how often do those collisions happen. This is just asking, what is the number of moles that get converted per second? So what's the number of moles that get formed per second? So this is a very summaric view of the reaction. Okay, just going to the question. Okay, that's fine. Okay, so you've got a summarized view of the rate of the reaction, right? You've summarized everything going on in the chemistry into one rate of reaction. And that's all well and good. It will help us make lots of progress very quickly. But I wanted us to think a bit about the fact that there's a certain probability that influences things. It has a bit to do with the contact between the molecules. And you see, all these are things that are going to affect us later on. So, but for now, just know that the reaction rate is expressed this way, right? Moles per second. So what's in 1 second, how much of the component is formed, right? So that's our default view of the reaction rate. And then we typically also base that on the volume. So when we think about the reacting space, right, if you take different samples of this volume, you could say, well, I could take just this subspace here, and there's a certain reaction rate that I get from that. Or I could take a bigger subspace, and then I can measure the reaction rate there, and so on. So you see, the amount of material, the amount of reaction volume that you consider is going to change the extent of the reaction or the rate of the reaction. So to avoid that, right, to avoid the fact that as you use different amounts of reaction volume, you get different rates, to avoid that issue, we just say per cubic meter. So instead of instead of having to define every time how much space, how much reaction, how much of the reacting species you have to consider, we just take a 1 cubic meter basis, and we say, clearly, then this is the rate we get for 1 cubic meter of that reacting mixture. Okay, any questions or comments there? Okay, and I'm just checking here. So in fact, then let's look at the question again. So if RA is the rate of formation of A, then what are the relationships between RA, RB, and RC? Right, and of course you can see here, you've got 2 of A reacting with 1 of B. So what does that mean in terms of these rates? And first of all, we can see it's written in terms of the rate of formation, right? We've defined Ri to be the rate of formation of something. And here you can see that A is not forming. In fact, A is a reactant, so A is being consumed. So a little notation trick that we often use in reaction engineering is we just write this as minus Ra. So this is then the negative rate of formation, if you like, or another way to say it is the rate of consumption. A. And in fact, you'll find that most of the time, we are talking about the rate of consumption of some reference component. So we can pick any of our species, right? You've got 3 species here, A, B, C. We could pick any one of those as the so-called reference component. So we could do all our calculations in terms of how much of A has converted, or how much of B has converted, or how much of C has formed. But most of the time, we just write minus RA, and we pick our key component, and then we just base our calculations on that. Right, so in fact, here, it's not clear what this means, right? When we write K equals this value right next to the rate expression, this doesn't tell us what, this is not enough information to work out the rate. And that's because we don't know which component this K refers to. We have to specify that this is the kinetic rate constant when we consider either A being consumed or B being consumed or C being formed. So we have to be very specific about the components that we are writing our equations over. Okay, so now we want to know what's the relationship among these three rates. So maybe just take 30 seconds and write out for yourself what you think the relative rates are. So you can write it something like RB equals something RA, and then RC equals something RA. Right, take a few seconds, just fill in the question marks there. I'm going to nitpick, I'll make a question mark sub 1 and mark sub 2. Okay, anyone want to volunteer there? That's the sound of me scrolling, hopefully for a raised hand, but nothing there. Okay, so in fact, let's look at the easier one first. So if you look at A and C, you can see they are being formed in equal amounts. All right, 1 second. Okay, so thanks to Jonathan. So RB is 1/2A. Right, so that's good. So we'll look at why that is now. Okay, so first you can see RA and RC. Those are going to be, those are equal in magnitude, right? So as you consume 1 mole of A, you will get 1 mole of C. So because the stoichiometric coefficient in front here is the same, then we can say they are equal in magnitude. However, the formation rate of C is equal to the consumption rate of A. So the formation of A is negative here. So we need to write it this way, right? So this minus RA, that's the rate of consumption of A, and RC is the rate of production of C. Okay, so that's one. Then in terms of RA and RB, you've got both are being consumed, so they will have the same sign. So in fact, strictly speaking, we should say minus in front of each of these. And then you can see that B is consumed half as fast as A. So whatever the rate is of A, B is half that rate. So if you like, RB equals a half A. Right, so that's why Jonathan says it's RB equals a half A, half RA. Right, now so we have to figure that out, and you can see it's quite easy to make a mistake there, right? Some of you may have written RB equals 2RA. So in fact, the general rule we can write is that we can write R sub I divided by nu sub I. Right, so nu is the stoichiometric coefficient, is equal to R sub J divided by nu sub J. And you can see that works for everything here. And of course, nu is also negative for reactants. Coefficient, and it's negative for reactants and positive for products. So you can write here R sub A divided by, and the stoichiometric coefficient for A is -2. That's equal to R sub B, and its stoichiometric coefficient is -1. And then you've got R sub C, and its stoichiometric coefficient is a +1. Okay, so that's how we can relate them. Okay, if the reaction is elementary, what's the rate expression? So I expect from the chemistry course, you'll have covered this, but what we might do is I'll dig up those notes and just add them. But in an elementary reaction, we look at the reactants and we take the concentration of each of the species and raise it to the power of that component. So if this reaction is elementary, and if it's a forward reaction only, right? So we didn't mention that. You can see the arrow only points to the right. That means the return or the reverse reaction of C going back to A and B, which can happen, right? You can get the product breaking down to give us the reactants again. In this case, it seems that doesn't really happen. So when we write it this way, we are saying that the forward reaction rate is much greater than the possible reverse reaction rate. So we are only considering a forward reaction rate here. And in terms of elementary reactions, we can then say that this is equal to, so we can write minus RA equals K times CA. And the coefficient for A is 2, and then CB, and the coefficient there is 1, right? And if we want to generalize that a bit, we can say, generally speaking, RI equals the product and it's going to be K J raised to the power, and I want to say here absolute of mu sub J, and then there's a kinetic constant there in front. Right, so so generally speaking, for an elementary reaction, we can say that the rate of formation of, or the rate of consumption, this will usually be a consumption rate. The rate of consumption of your component is equal to the product of all the concentrations of the reactants raised to the power of the stoichiometric coefficient. So we need to look back at our basic chemistry notes to look at how this is derived. So this is derived quite nicely. Here, I'll dig out those notes. So that's what we can do for if it's elementary. And that's something I didn't mention also, that the reaction rate can be anything, right? There's nothing to say that for this, even for this specific reaction, right? It might have turned out that R sub A is not dependent on anything. So maybe R sub A is just a constant like this, that no matter how you change A and B, the reaction just stays constant. Or it might be, well, that the rate is actually only dependent on the concentration of component B, and it might well be it's the concentration of B raised to some weird power. So our rate expressions, they are not all elementary reactions, right? So it's easily the case that our reaction rate is some other form, some unexpected form. And that happens when our reaction steps are not broken down. So if the reaction is as simple as this, where 2 of A reacts with 1 of B in one step and gives us 2 C's, if that's all one step, then that tends to be an elementary reaction. But if there are multiple steps involved, and it might well be that the reaction of the 2 A's is extremely fast. So it might be that A combines with A extremely quickly. But this step where the 2 A's and the B reacting, if the adsorption of the B onto the double A complex is slow, then the reaction might, it might depend more on the concentration of component B. So for lots of real reasons, right, not just because we fit the rate and we get some weird equation that fits better, for real reasons, for chemical reasons, it might be that the rate, the observed rate, the rate that we want to use for our expression, right? If we want the rate to summarize everything going on, then it might not be an elementary reaction. But in a happy situation where we have a simple expression and it tells us everything that's going on, then it's good enough to, and if it works out that way, then it's an elementary reaction. So I'm saying that in a long-winded way, but what I'm trying to say here is that it's not automatic that a reaction is elementary. So it's not the case that even if you are given the reaction expression, that you can assume that it's an elementary reaction. It's extra information. So you have to be told the reaction is elementary. So that's why it's written in this way. If the reaction is elementary, what's the rate expression for RA, right? Then C here says, if it's reversible, then what's the rate expression, right? So we know the forward rate. So A is consumed in the forward reaction, but then it's possibly the case that C also breaks back down into A and B. So to estimate that, and you see there again, we need extra information. This doesn't give us all the information, right? We've so far only been told that the forward reaction is elementary, right? We don't know what the reverse reaction conditions are. But let's assume that the reverse reaction is also elementary. So if so, then in the reverse case, we get, then the thinking for the forward reaction still holds, and then we just have to add in the contribution from C. So in the C case, we write a new expression here, and this is going to be CC. So we are assuming this is elementary. And now let's think about what's happening here. If it's the reverse reaction, then C is breaking down to give us back A, right? So the reverse reaction results in the formation of A. However, we are writing this in terms of the consumption of A. So we need a double negative here, right? We need to say this is going to reduce our consumption of A because it's going to form A. So that's going to be the expression that we'll use there. Even there are a couple of things to be careful with. Okay, this example doesn't show what I had in mind. I wanted to say you have to be careful there again that that you are using the right coefficient here. So let's say this was 3C, right? Then you have to use the right stoichiometry. So you have to know what this refers to. So if this is the rate of formation of A due to the reverse reaction, this is fine. But if this was the rate of formation of B, let's say, so for whatever reason, if you created KR, so that was the formation of B, and A is twice that, then you have to be careful and write the right coefficient in there. So what I'm trying to say there is your rate expression, you have to know what component that is based on. So here we based it on the consumption rate of A, and then here we talked about it for the rate of consumption of C. And because C consumption equals A production, then that's fine. There's a 1 in front here. Okay, so any questions or comments there? Okay, then question 2, what's the rate of this reaction? So we have a rate expression now, and we have concentrations. And of course, I'm going back to this form. So this is what we are actually, so far what we've actually said the reaction rate is. So we have this expression and we have K specified. So we have a number for K, and then we've got concentration. So you can just stick the values in here and that will give you a reaction rate for A. And then what's the speed of the reaction? And there again, we talked about this earlier. We don't know what that means exactly. Is it the time taken, right? And speed is not time, of course. It's closer to frequency. In catalysis, you have this concept of turnover frequency. So for one molecule, how long does it take to convert one molecule? Or rather, it's the amount of time that a molecule spends on an active catalytic site. Anyway, there are all kinds of different definitions that go into figuring out what we mean by the speed of the reaction. So I just wanted to point out here that the rate is something we can evaluate easily. The intrinsic speed of the reaction, that comes down to what is the time taken for the steps here to occur. And we can't easily figure that out. We can't answer that question, right? We have a rate constant, and that doesn't tell us anything about the speed. Well, it is the product of the speed, but there are a bunch of other things that go into that rate constant. So we can't answer this part of the question. We don't know the speed of the reaction. What's the probability of the reaction occurring? And in fact, there is something we can talk about towards this, right? So the probability of the reaction occurring, number one, we know it's an elementary reaction, right? And if it's an elementary reaction, then we do have this expression. And so we can see here that the concentration of A, as that increases, the rate will increase according to the square of that. And then as B increases, RA increases linearly. And then we do have the concentrations in this case. So we can at least compare it to the probability of a different situation. We can say if CA is 2 and CB equals 5, we can work at the relative probability. We can say we have some number for this situation, and we can compare it to a different situation. And we can say, yes, this case is more probable than that case. But we can't answer with an absolute probability. We can't say 0.5. And in fact, it's a bit of a nonsense question, right? If the reaction is possible, it is going to happen, right? You've got 10 to the 23 molecules in 1 mole, right? That's a crazy amount. That's an amount, right? 10 to the 23. You can hold 10 to the 23 molecules between your fingers. And so even with the, 1 cubic, centimeter, in 1 cubic centimeter, even if your reaction rate is very low, this reaction is going to happen. So in fact, an answer to this is 100%. Definitely this reaction is going to happen, right? There's no possibility it's not going to happen. There are so many molecules in such small spaces. And here it's not even that the concentrations are very low. So definitely the reaction is going to happen. Okay, then how long will it take to convert 50 moles of A? So now it starts to look reasonable. This starts to look like more of a reasonable question. We have a reaction rate. We can work out a number. We can stick 3 and 4 in our rate expression. We can stick the constant in, and that will give us a number. And we know that the moles of A will change by 50. So let's write this. We can say here delta in A equals, and it's consumed, so minus 50. So to convert A, and we have initially 3, so we can say CA equals 3. Let's write the units, so moles per cubic meter, and this one is moles. And we've got RA, which is something, right? And the units are moles per second. Moles second moles a second per cubic meter, right? And we are given a time, 1 hour. T equals 3,600 seconds, right? But you can see here that when you multiply the rate by the time, you're going to get moles per cubic meter, whereas what we want is something like moles. So we need a volume as well. So we need to assume something here. So missing the volume. So we need the volume V. I'm pointing this out because it's a common mistake, right? Quite often you'll find you'll make a mistake missing out the volume. So anyway, what we can write now is the rate times the volume, RA volume, times the time. That's going to be the change in the moles. Right, or rather, what does it ask? How long does it take? So we don't know we don't know the time. We're trying to work out the time, right? So we can work out the time from this equation. We can say the change in moles of A equals the reaction rate times the time. That one's obvious, and then we have to be careful to get the volume also. So you can work that one out. Okay. And now something also to talk about, I guess this should be the last thing, is that our kinetic rate constant here has these weird units. You can see here moles per second per cubic meter per moles per cubic meter cubed, right? And that's because you see our rate expressions, we said, can change depending on the nature of the reaction. Right, so and here you can see you've got concentration cubed, right? You've got 2 from A and 1 from B. Here it's constant, so no concentrations here. And then here it's concentration raised to the power a half. Now the rate can't be changing in its units all the time, right? And if you think of it, it is a well understood thing, right? The rate, it's moles per second per cubic meter. That's our definition of rate. We can't change that. We also can't change our definition for concentration, right? Moles per cubic meter. We don't want to tamper with that. So those are fixed. So the only free play we have is in this constant K. So this K will have different units depending on the order of the reaction. So we count this as a third order reaction, 2 from A and 1 from B, or it's better to say it's second order with respect to A and first order with respect to B, but in effect, it's third order. And so you've got concentration cubed here. And now you want moles per second per cubic meter here, and you've got concentration cubed. So the units of this K are going to be moles per second per cubic meter divided by concentration cubed units. So that's why it's written in this weird way, right? You can see up here, the units for rate, moles per second per cubic meter, and then you've got moles per cubic meter, so that's concentration, and then it's third order because it says it's elementary, and if you count here, you can see that's going to be third order. So it's concentration cubed, so that's why the units look like that, right? And so just to note then, to always be very careful with your units on K. It is going to depend on the nature of the reaction. Okay, and then, well, the last one, maybe we'll stop there now. But here, you can think about that A is being consumed and B is being produced. But think about the fact that as A is being consumed, the rate is going to change, right? So your rate is it has a quadratic dependence on your concentration of A, right? Your rate has that squared dependence on A. Sorry, 1 second. Yeah, so my child wants to post a Roblox video. So anyway, so here you've got your rate. It has a squared dependence on the concentration of A, and so in the question here, we can think about as the reaction proceeds and A and B get consumed and C is produced, how is that concentration going to change? We know it's going to drop, but maybe try and go further and actually sketch the shape of what that's going to do. Another interesting one here, what's the pressure going to do over time? Right, and so it says it's a gas, so this reaction is happening in the gas phase. So maybe can you tell me quickly, what's the pressure going to do in this case? Stay the same, go up, go down? So maybe thumbs up if it goes up, thumbs down if it goes down. Okay, so let's if you don't give an answer there, then that means you've all got it wrong, right? Okay, let's see, who do we have? So thanks, Jonathan. The pressure drops. Do you want to tell everyone why that is?
I think it's because as A and B are fed into the reactor, the pressure that was initially there is slowly dropping as they are being consumed to form T. That's the way I put it.
Thanks, Jonathan. So yeah, basically you've got 3 moles of 3 molecules becoming 2 molecules. So if you like, you have 3 molecules banging around against the walls of this vessel, becoming 2 molecules banging around. So the pressure is dropping. There are fewer molecules free floating in the space. So the pressure is going to drop. Just your net change is for a smaller number of moles. If you like, you can always just look at your ideal gas law. So you can ask, what would the ideal gas law do? How do you say it? WWTIGD. Okay, so it doesn't roll off the tongue really well, but yeah, I often just think about the ideal gas law. What's happening if this was the ideal gas case? And so we know we've got PV equals nRT. And so you've got your number of moles, your total number of moles going down. So clearly, if everything else is constant, if we assume temperature is constant and volume to be constant, then if N is going down, P must also go down. Right, so pressure should be dropping over time. And this last one, can you answer that? Sketch the temperature over time. And you see the answer to that last one is really, it depends. So you can't really work out the temperature unless you know the relative energies. And here you can think about your thermodynamics knowledge. Let's just write this thing out. So what we have here is simply a reacting gas. It doesn't say anything about heat being added or removed from the system. So there's no heating or cooling here. It's the reaction itself that might change the temperature. And so what we want to think about is what's the energy state of this? So is the internal energy, right? Think about the terms that you've learned in thermodynamics, right? The enthalpies of A and B. Is the net enthalpy going to be higher before when compared with after the reaction? So if C has a lower enthalpy, then that means the energy locked into the molecules will be lower, right, than at the start. So at the start, you had A and B only. And locked into the molecules of A and B, there's a certain amount of energy. And then when they get converted to C, if C has a lower energy potential, then in order for the total energy to be the same, you will have to give off energy to the environment. So that will show up as heat. So if you like, there are two forms of energy here. One is the internal chemical potential energy. So we think of that as the structure of the molecules. To keep those molecules intact, there's a certain amount of energy. And then there's free energy in the atmosphere. So all the molecules bouncing around, the kinetic energy of the whole body of molecules. So that's the kind of thermal energy. So thermal energy and chemical energy. So if your chemical energy is lower, that means you must have given off more heat to the environment. And so your temperature will rise. And of course, we can't know whether it's lower or higher without looking at the enthalpy. So that's the missing information there. We need to know about the enthalpy in the system to answer that. Okay, so I guess we've actually worked through everything, but maybe just go through the questions yourselves. And this is something I say repeatedly, until and unless you work through the problem yourself, you won't know where you are going to get stuck, right? And when you read a solution, it's very, very easy. You'll think, yes, that's obvious, that's obvious. But when you actually separately try and do it without looking at a solution, you suddenly discover, oh, wait, I don't know what to do at this point. And then you're just stuck. So that's why you have to practice these things, figure out where your stuck points are, and work through that. So I guess that's it for today. The question, will you be uploading the lecture to Dropbox? So yeah, so I guess it's the video. Yeah, I'll stick it on YouTube with the rest. And I guess these notes that I've been writing in here, I'll also put that on Dropbox. Yeah, I sometimes get attendance problems, no problem. I sometimes get attendance problems when I make things so easily accessible. So yeah, we'll put in some kind of attendance registering and all that kind of silly stuff. Okay, I guess that's it. Any questions, anything unclear, anything we should talk about as well? Okay, if not, thanks very much, everyone. Thanks for attending, and I'll see you next time.